Hello everyone. So here's a brief description of waves as they're taught in the introductory physics for engineering and science majors. Let's consider a plot which gives the displacement of a bunch of particles participating in a wavy motion. While we usually look at that picture and think of a wave, we have to remember that this is just the way how the wave looks at one given time. A little bit later, consider the point at the origin here of my coordinate system is actually moving away from its equilibrium, and yet even later it's farther away until it actually reaches maximum displacement. Then it's going to stop briefly and then continue coming back towards equilibrium. In the process, the wave appears to be actually moving to the left, in other words, in opposite direction to our positive direction for x. So the description of all those particles and how they move is given by the displacement, which is a function of the position x of each particle, how far it is from the origin of the wave, and the time. You have to see this x, and you have to remember that x is not it's slightly different from what we are used to in our physics class, because here x is not just a continuous function of a position of a one particle that is moving through space, but it's actually the distance of each of those particles along the wave measured from the source of the wave. So this x is actually being used to pinpoint to all those particles that are participating in the motion. It is a very important distinction because it underlies the fact that there is no matter that is actually being moved from one place to another. Waves do not move matter, they actually move energy. The matter just oscillates at one given position, and in our case here is x. Take, for instance, the position for which we have x equal 10. That means we are now focusing on the point or the particle that is 10 meters away from the source of the wave and how it actually behaves and oscillates around its own equilibrium. As in oscillations, we will have this characteristic time called period, which gives us the time for one cycle of each of those particles as they oscillate about their own equilibrium. Remember, we also have frequency associated with period, which gives us the number of cycles or oscillations every second. And of course, we have the relationship between the two, period being always equal to 1 over the frequency. We also have the concept of angular frequency. We use the Greek letter omega measured in radians per second, and from oscillations we already have the relationship between omega, the period, and the frequency. Here it is given again as omega will always be equal to 2 pi over t, the period of oscillations of all those particles along the wave, or also omega is equal to 2 pi f, which is the frequency in hertz. So let's look at the new aspect here. We have many particles participating in periodic motion. The new element here is that they're spaced out and there's a characteristic length. In this particular picture, I have marked that length from a trough to another trough along the wave. In other words, between two particles that oscillate in an identical manner. And we're going to call that spacing a wavelength. The wavelength can be measured from two crests, adjacent crests, or from any point to the next adjacent point, as long as the next point has identical motion to the first one. And so here is the function for the displacement of all those particles participating in the wavy motion as a function of their distance from the source x and the time t. We have this constant, in this case g naught, which is their amplitude, the farthest they're going to reach from equilibrium, multiplied by the sine function. And the argument of the sine here is kx plus omega t plus phi. Here d naught is the amplitude, or how far a particle goes away from equilibrium. K is the wave number measured in units of 1 over m. Phi is some free parameter called the initial phase angle. Sometimes we need to have the freedom to add some constants into that argument to fit particular conditions for our waves. And let's look at an interesting pattern. The waves have symmetry, that actually the waves repeat themselves not only in time but in space, where in time we have the period t. In other words, a particle will complete its motion and repeat identical second cycle after t seconds. In space, we can actually go down the crests or the troughs of a wave, and we see that if we go over a distance equal to the wavelength, we will see a particle moving in identical manner. And so whatever omega serves in time, as omega is equal to 2 pi over t, the same function here is served by the wave number k, only in this case is going to be k is equal to 2 pi over the spatial period, if you wish to call it that way, 2 pi over lambda. For a wave traveling along the positive direction of x, the only difference in this case is that we need to write the function with a minus in front of omega. So in other words, as we were moving along the waves and we saw that picture in the beginning, we had to subtract from the argument in order for us to see a wavy motion that appears to be going to the right. So let's look at what that velocity of the wave is. Given that the wave does not move any particle or matter from one place to another, you can have an earthquake in the middle of the Pacific, but the water that is going to show up on the shore is not the water from the middle of the ocean. Only energy is being transported by the waves. So how shall we determine what that velocity wave is? So let's go back again to that picture of the waves, and this time I'll consider a point somewhere around the 14-meter mark. The point is at the crest of the wave, but a little bit later another point becomes the crest, because the original point at around the 14-meter mark is now moving towards its equilibrium. Yet a little bit later another particle is along the crest of the wave, and so you can see how the crests are actually moving towards the left, while the actual physical matter, particle, or substance is simply oscillating up and down according to the diagram. The question here then becomes how fast are those crests moving through space? Let's look at the function for the displacement, which was d naught sine of kx plus omega t plus phi. I used here plus for the omega t term because, again, I'm still working with a wave that appears to be moving to the left, in other words, opposite to my positive x direction. At the wave crests for any point, the argument of the sign has to be a fixed value. Just think about it. If one point at the crest has some value of kx plus omega t plus phi equal to 5 or 10, a little bit later its neighbor will become the crest. It will have the same displacement, which means that next moment the neighbor has the same argument as the original particle. So we see that as particles one after another become the crests, they all have to have that argument having the same value as the original particle. So I'll write this expression as kx plus omega t plus phi equal to some constant. We don't care how much it is. The important thing is that it's some fixed value as the crest goes from one particle to another to another. So going back to the velocity, the question in this case, we can actually ask ourselves, well, how fast is the crest moving across the particles? In other words, I can look at the rate at which the position of those particles changes with time, and so we end up with our usual and typical expression for velocity as the rate at which the x changes with time, or in other words, the derivative of x with respect to time. Going back to our relationship about the crests and the argument of the sign for particles that become crests, we can see that we can easily find that derivative of dx dt. Simply we'll just differentiate the expression, and that will give us that k dx dt plus omega. Remember, the derivative of omega t is just omega, will have to be equal to 0 since phi and the constants are just constants, so they'll disappear in the differentiation process. That of course, gives us for the velocity of the wave, which has to be dx dt, simply equal to minus omega, the angular frequency, over k, the wave number. Here we got a minus, which is very natural because remember, our wave is actually moving to the left or opposite to our positive direction for x, the way we chose it. If we were working with a wave that travels in the positive direction, then we'll have the velocity for that wave simply equal to omega k. If we remember that omega and k were related to the period and the wavelength of the wave, then we can actually replace omega and k with the period and the wavelength, and we arrive at the formula for the velocity that is equal to the wavelength over the period. This is a very interesting formula because it actually tells us that the wave travels exactly a distance equal to its wavelength in a time that is exactly equal to the period or the time for one particle, each of those particles, to complete their cycle. This formula is actually written more frequently in terms of the wavelength and the frequency. So I wrote it here for you as v is equal to lambda f. Remember that the 1 over t, or 1 over the period, is equal to the frequency in hertz. This is a very important formula and we'll be using it a lot of time. And so I guess if you had to remember one formula from physics, I would recommend that that is the one.